We talked about the covalent bonds and the molecular geometry related to the electron densities of covalent bonds. Now we need to know about the energies of the chemical bond. To understand this part, we need to be familiar with the dual nature of electrons. Light consists of particles. We call them photons. Those photons move in a wave motion. Einstein described the energy of photons, E, to be proportional to the frequency of light, with the H proportionality constant, Planck constant. Afterward, de Broglie proposed that if the light, which is an electromagnetic wave, exhibits properties of particles, this means any particle should exhibit wave properties. This is what we call the dual nature of particles. This means particles such as electrons have wave characters. For any particles, the wavelength of a particle, lambda, and a mass, m, is related by the equation the wavelength, lambda, equal to Planck's constant over mass, m, multiplied by the frequency, mu. From this principle, Edwin Schrödinger proposed an equation to describe the wave motion of an electron in an atom or a molecule. The sets of solutions of Schrödinger equation, the wave function, Greek psi, each defines the energy of an electron in the region of space it may occupy. This region's three-dimensional space is referred to as orbitals. Each orbital contains two electrons with a wave function value psi square. This means the value of psi square is proportional to the electron density at a certain point. For simplicity, we describe orbitals as a solid mesh where the electron density is contained. But by now you know that orbitals are the space that if you use the wave function, you can predict the location of an electron at a certain time. At a certain time, because electrons move in a wave motion around the nucleus in a continuous motion. Time and space describe the location of an electron. Let's learn more about orbitals, in specific the s and p orbitals, that are mostly associated with the valence electrons and electron pairs. We saw in the second lecture how we arranged the orbitals in subshells according to their energies. Because most valence electrons are in the s and p orbitals, let's learn more about the shape of s and p orbitals. First, s orbital is symmetrical along all axes. That is why we present it as a spherical mesh. Notice there are two spheres and two s. The two spheres represent the two s, two phases. In phase, when two electron waves overlap adding up constructively, or out of phase when the two waves add destructively. Remember we said that the probability of finding electrons is equal to the square of the wave function, so it is always has to be positive value. Psi can be either negative or positive, but psi square has to be positive. The two spheres represent the possibilities of finding the electrons. Now moving to the p orbitals. We have three p orbitals, bx, by, and bz. In here we can see the three-dimensional representation of the two p orbitals. Each orbital is represented as two loops. The three orbitals are perpendicular to each other. The sign of the wave function is positive at one loop, negative at the other, and equal to 0 at the nucleus.